Hello, my name is Gabriel Kapchuk. I'm here today to talk to you about efficient set membership proofs using MPC in the head. And this is joint work with Matthias from Aarhus University and Arushi and Matt from Johns Hopkins University. In this work today, we're going to be talking about set membership proofs or set membership statements. These are statements or proofs in which a prover wants to demonstrate that X1 through XL, these are all publicly known elements, that one of them is in the language L. And we're also going to be using relation circuit notation here, so R being the relation circuit corresponding to L. And we're going to be using alpha to denote the active branch, that is to say, the index of the instance that the prover actually knows the witness for and is going to be using to actually satisfy the zero knowledge proof. Good. So why care about set membership proofs at all? Set membership proofs are really important for privacy preserving systems. And that's because in some cases, zero knowledge isn't enough to actually give you privacy. That is to say, by simply generating a zero knowledge proof, it might reveal something about who you are. So take, for example, if I give you a zero knowledge proof that I can produce a signature on some particular message under a given public key, that might reveal that I hold that secret key and therefore reveal my identity. In order to kind of overcome the situation, set membership proofs have been used for a long time. Ring signatures are a great example of a set membership proof. And these are signatures in which a prover wants to hide their identity among a set of public keys. So in this case, PK1 through PKL. And they can generate a signature and show this signature validates under one of these public keys, but I'm not going to reveal which of these public keys it is. And therefore, you're not sure who the signer is from that publicly known set. This notion of privacy has been used in a lot of deployed systems. For instance, Monero and Zcash both use some kind of ring signature or set membership proof in order to give privacy to those sending and receiving transactions on the blockchain. In our work, what we do is we put forward a framework for integrating efficient set membership proofs into MPC in the head protocols. We show how to actually integrate into existing MPC in the head protocols efficiently. And we give some applications of these systems, in particular, the smallest known symmetric key post-quantum ring signatures. And we also give an extremely simple construction of ring CT transactions that are post-quantum from basically just building on top of this signature. So everybody's on the same page, we'll quickly review the ICOS framework for MPC in the head. This is a family of zero knowledge protocols that work vaguely like this. So a prover will start by emulating an MPC. The function that is being computed inside of the MPC is the relation circuit for the relevant language. The prover will then commit to each of the emulated parties' views and send the commitment to the verifier. The verifier will then challenge a subset of the parties, and the prover will open those subset and send them to the verifier. In order to be convinced that the parties acted honestly, the verifier is going to check for consistency among the parties' views. So if a message was sent from one party to another, the verifier will check that that message is represented honestly in both commitments. So how are we going to integrate set membership into this paradigm efficiently? We're going to start with some inefficient approaches. So the first is a naive repetition of the relation circuit. So in this case, what we'll just do is line up L copies of the relation circuit, evaluate each one on a different instance xi, and then OR the outputs. While very, very simple, this is incredibly inefficient, right? Because we're going to get L copies of the relation circuit, which might potentially be very, very big. And so there's a multiplicative overhead in L. Something that's actually that's much better is we could kind of separate out the logic for doing the set membership from the relation circuit. So in this case, we have on the left-hand side of our circuit, the relation circuit being evaluated. So here its inputs are the witness W along with a secret instance X alpha. In order to check that X alpha is one of the set X1 through XL, what we'll just do is an element-wise equality check and then OR the results of those equality checks. This is more efficient, but there's still a linear number of equality checks happening in the circuit, and L could actually be quite large, think 2 to the 15, right? And so this would not be something you'd want to do in practice. What you'd really want is something that's sublinear in L. The way to get sublinearity in L for the general approach is to use some kind of accumulator, like a Merkle tree, in order to do the set membership check. So here, the left-hand side of the circuit remains exactly the same. We're going to feed in the secret element X alpha along with the secret path into the Merkle tree authenticator, along with a publicly known root that represents the accumulation of all of the public elements of the set. And then simply check that the Merkle tree authenticator is correct along with the circuit R. From an asymptotic perspective, this is great. The Merkle tree authenticator can be represented in a logarithmic number of gates in L. The problem is that that asymptotic hides a bunch of really, really, really high constants. In particular, we're going to do log L hashes, and representing hash functions as gates can be incredibly, incredibly expensive. So what we're going to do in our work is take this basic Merkle tree approach. What we're going to try and do is take the Merkle tree authenticator and move it outside of the circuit that's going to be evaluated inside the MPC in the head. And because it's going to be outside, we're not going to need to represent it as gates, and we're going to be able to run it at hardware time. Good. So the first step in order to achieve our approach is to use a pre-processing similar to the one proposed in KKW. It was proposed in KKW in order to be able to use a more efficient MPC. We're going to use it for slightly different reasons. The idea here is that the MPC that's going to be run inside the prover's head is going to be in a pre-processing hybrid model. And the pre-processing is going to descend from some central coordinator, and the parties are going to be able to use it during their evaluation of the circuit. Commitment is going to kind of look similar as before. The prover is going to commit to all the parties' views, but they're also going to commit to some pre-processing seeds. And we're going to use this commitment to do a cut and choose style argument that says that the pre-processing is done correctly. What does that mean? That means that the verifier is going to challenge both a set of views, but also a set of pre-processings to make sure that the pre-processing was done correctly. And the prover is going to open the pre-processings that were challenged along with the views. And the verifier will check for correctness and consistency. Good. So how are we going to use this approach to get set membership? For the next couple of slides, we've got the dividing line. This dividing line, everything that happens below it is going to be during pre-processing, and everything above it is going to be happening during the online phase of the emulated MPC. So because the pre-processing is going to be validated using a cut and choose approach, note that everything that happens there has to be privacy free. It cannot in any way depend on the witness. So one kind of natural way you might want to try to use a pre-processing phase is in addition to pre-processing for efficiency in the online MPC, we're also going to create secret shares of all of the publicly known values x1 through xl. Then during the online phase, we're going to take one of those secret shared values, reconstruct it to get x alpha, and then evaluate the relation circuit on x alpha. This is basically what we're going to be doing in this work, but this strawman approach doesn't quite get where we need to go. In particular, you'll notice that this is in no way zero knowledge, right? Because although all of the values have been secret shared, the verifier can just check the index of the secret share that's used by the parties, and they'll be able to figure out what alpha is. So we need to do a little bit more work in order to get zero knowledge. In order to do this, what we're going to do is something very intuitive. We're going to take these secret shares and we're going to shuffle them during pre-processing. Note that the elements x1 through xl are all publicly known, and the shuffle is going to be verifiable during cut and choose. That is to say, the verifier can check that it represents an honest shuffle of those elements. But during the actual pre-processings that are going to be used during the online phase, the shuffle will not be known. So this works. This gives us zero knowledge. This gets us most of the way where we want to go. The problem is that this is not communication efficient when instantiated inside of an MPC protocol. In particular, because sending the list of x1 through xl, even when shuffled, is still linear in L. Just the number of secret shares that each party needs to have is linear in L. And so this ends up being not communication efficient. So we need to do a little bit more work in order to get communication efficiency. The idea here is we're just going to do a slightly fancier version of the pre-processing that's really all about the same core intuition. What we're going to have happen is the coordinator is going to generate a secret sharing of a random value R, is going to use this value to mask all of the known values, publicly known values x1 through xl. These are then going to be shuffled and then accumulated into an accumulator. You can think about this as a Merkle tree. I'll use notation as though it's a Merkle tree, although in principle, it works just fine with other accumulators as well. During the online phase of the MPC, we're going to use some of the outputs of this accumulation process as public inputs to the MPC. That is to say, this value R plus X alpha is going to be used as a public input. Additionally, what can happen is we can check to make sure that this R plus X alpha really did come from the pre-processing. And we can do that check without having to use any of the MPC and the head techniques. It can happen completely in parallel. So we're going to give a root, a path, and R plus X alpha, and verify that these correspond to the pre-processing that happened during this run. Importantly, R plus X alpha is distributed independently of X alpha, and so it does not reveal anything about the value of alpha. In the actual emulated MPC, what will happen is we'll take the public input R plus X alpha, as well as the secret mask R, and we'll use the mask to recover the actual value X alpha, and we can then feed the secret value X alpha into the relation circuit and get the output 1. This is the high-level approach that we use, our template for making this work. And you'll notice that the big idea here is that we've taken the Merkle tree verification and moved it outside of the circuit. And importantly, this gives us logarithmic communication complexity, right? Because the only thing, R plus X alpha and root are both constant sized, but path here is logarithmic in L. So to see how this works out, let's look at NISQ-based post-quantum ring signatures from symmetric key assumptions. These are a primitive that have been known and used in the last couple of years and are represented in the NIST PQC competition that just finished. In order to get basically, it's a zero knowledge proof that the prover shows that they have a secret key, such that the PRF evaluated with that secret key at the point 0 equals some known public key. In order to bind the message M into the zero knowledge proof, it's put into the fiat shamir during flattening. In order to get a ring signature version of this, KKW just showed that you could add a set membership to the zero knowledge statement. In order to realize this ring signature, what they did is that they used the exact Merkle tree authentication trick that we had shown before. And in practice, you can see from their results that the size of the number of gates that are added from this authentication check significantly dominates the size of the circuit. And in general, it's log L times the size of a low MC circuit, where low MC is used as the PRF. In our implementation, what we do is use the same framework that we had before. So during pre-processing, what will happen is this random mask R is applied to all of the public keys. These public keys are shuffled, accumulated, and then the prover, the signer's actual PK is pulled out and used as public input in this masked form to the MPC in the head. It's then unmasked. Low MC is run on the prover secret key and the point 0. This results in some potential public key, and we check for equality between PK alpha and the output of low MC in order to finish out the circuit. We find that this produces very small symmetric key signatures. Because they're symmetric key, they're plausibly post-quantum. We find that our signatures are about 1/5 to 1/8 the size of KKWs, depending on the exact size of the circuit that you are interested in. We can also compare our work to other lattice-based post-quantum ring signatures. At the time we initially submitted our work, ours represented the smallest post-quantum ring signatures, even comparing against lattice-based constructions. But in the last year or so, lattice-based constructions have gotten smaller and smaller, and now are smaller than our constructions. There's several things that I didn't have time to talk about today in my talk. We show how to integrate our approaches in a non-black box way to specific MPC in the head protocols to get even better efficiency instead of having a very generic approach. We also give this very super simple, very efficient post-quantum ring CT construction that's really intuitive. The high-level idea there is that once you get zero knowledge that can support set membership easily, most of the difficult problems in ring CT just immediately disappear. And with that, I'd like to thank you for your attention.